Is the game show Deal or No Deal an instance of the Monty Hall problem? Let's run a simulation in Python to find out. First, some background. I'm going to assume at this point that everyone is familiar with the Monty Hall problem, so I won't belabor on that. If you need a refresher, here's a link to a number file video. But in case you aren't familiar with Deal or No Deal, here's how it works. At the start of the game, you're presented with 26 numbered briefcases, containing prizes ranging, in the American version, from 1 cent to $1 million.
$1 million.
You pick one case to be yours, then spend the rest of the game opening the remaining cases one by one, revealing the prizes inside. At various points, a mysterious banker will offer you money in exchange for your case, leading to the eponymous Deal or No Deal. There's certainly some interesting game theory to be analyzed here, regarding things like expected value versus utility, but for the sake of this analysis, we're just going to consider the situation where the player rejects all the banker's offers, and is left with two unopened cases. The one they chose, and the one they didn't. The player is then given a choice. Do they stick with the case they chose at the beginning of the game, or swap it for the unopened case? On the surface, this looks like the Monty Hall problem. And so, to maximize your chance of winning, you should swap the cases. But is that really true? Let's find out. First, let's try simulating the normal Monty Hall problem, just to demonstrate. We'll write a function that takes in the number of doors, with a default of 3, and whether we want to swap or not, with a default of not. It'll return a Boolean value representing whether we won or not. Now, the code we're writing here isn't going to be the most well-written or efficient code in the world. Instead, we're going to try to capture the actual process of playing the game, with as few optimizations or simplifications as is reasonable. This should hopefully make it easier to see the parallels between the simulation and the actual game. So, we'll make an array representing the n doors. There are n-1 goats and 1 car. We'll then shuffle it, so we have no way of knowing which door has the car, and pick a random door. Now, it's Monty's turn. His goal is to choose one other door to leave closed, and open all the rest. In the normal case of there being 3 doors, that just means he opens one door, but we want this to be general, so instead of choosing the door to open, we'll have him choose the door to remain closed. He knows where the car is, so he wants to avoid opening that door. So Monty has 2 options. If you chose a goat, then he has no choice. He must choose the door with the car to remain closed. Otherwise, if you chose the car, it doesn't matter which door Monty chooses. He just picks randomly between the remaining doors. Finally, it's your turn once again. There are 2 doors left closed. The one you chose at the start, and the one Monty chose not to open. The only thing left to do is to swap doors, should you so desire. Then, we can return true if the car is behind your door, and false if it's not. Now, we can call this method and see if our strategy of switching pays off. Let's set it up so the simulation will run many times, say 1,000,000. First, we'll try 1,000,000 runs without swapping, then another 1,000,000 with swapping. It looks like we win about 1/3 of the time when we don't swap, and 2/3 of the time when we do, just like the math predicts. Neat. One neat thing about the Monty Hall problem is that it scales. So, we can win 2/3 of the time when there are 3 doors, but what if there were 26 doors, like the 26 cases in Deal or No Deal? Well, in that case, swapping leads to a win rate of about 25 out of 26. So, if Deal or No Deal truly is an instance of the Monty Hall problem, it seems like swapping is a no-brainer, right? In fact, if swapping really was such a good strategy, couldn't you all but guarantee a win by just holding out to the end, then swapping every time?
No deal. Before we open your case, I'm going to give you the opportunity to switch your case with the one remaining up there.
That doesn't seem quite right, though. Anyway, let's try writing the simulation to see what happens. Again, we'll write a method to simulate the game, but this time, instead of taking in the number of doors, we'll take in an array with the different prize values. We'll shuffle the prizes and make a list to store the case numbers from 1 to 26. Or actually, 0 to 25. We'll randomly pick our case and remove it from the list. Then, just like in the game, we'll open all the remaining cases one by one at random, leaving just one case. Obviously, we don't know which prize is inside which case, so there's no sort of strategy you can follow here. Finally, we decide if we want to swap or not, and return the value of our case. Let's again run the simulation 1 million times, and see what our expected winnings are if we swap, and if we don't. If we don't swap, we should expect to win about $131,000. And if we do, we should expect to win, again, about $131,000. So there you go. That seems pretty definitive. It doesn't matter whether you swap or not, so Deal or No Deal isn't an instance of the Monty Hall problem. But just to be thorough, let's try a couple more scenarios. What if instead of a gradient of prizes, it was more like Let's Make a Deal, with 25 bad prizes and just one good prize? Well, now our expected winnings are $38,000, but it still doesn't matter whether we swap or not. Or maybe Deal or No Deal in general isn't a case of the Monty Hall problem, but what if we consider just the scenarios like in this video, where there are 2 prizes left, one good prize and one bad prize? Let's try adding a short circuit to the simulation, which returns early if either our case or the one remaining case is anything but the 1 cent or $1 million prize. Most of the simulations will hit the short circuit, so to calculate expected value, we'll keep a tally of all the simulations that don't, then divide by that. And you probably saw this coming, but now the expected value is about $500,000. Swapping continues to not make a difference. So, the simulations are pretty definitive, but let's see if we can quickly build an intuition for why these two scenarios are different. First, let's look at the code for these two simulations. The difference between the two should be obvious. The Monty Hall problem is a 2-player game. Monty knows where the car is, and his door opening strategy factors that in. In Deal or No Deal, you just open the cases essentially at random. But why does that make a difference in the end? Let's ponder further. In the case of the Monty Hall problem, a useful Gedanken experiment is to consider the case with 100 doors instead of just 3. In this 100-door version, it's clear that your door has very little chance of being a winner. You just chose it randomly out of 100 after all. But Monty's door, Monty knows where the car is, and out of the 99 doors he could have chosen to leave closed, he chose this one. And the only way it could have a goat is if you happen to choose the car in the beginning. Given the choice, you should obviously choose the door that Monty picked over yours. Now consider Deal or No Deal with its 26 cases. For the sake of simplicity, let's assume that there are just 2 types of prizes, a good prize and a bad prize. Like in the 100-door Monty Hall problem, the case you choose at the beginning of the game is very unlikely to be a winner. The key difference comes with the second case, the one left behind. Monty isn't here to pick for you. You have to choose this case yourself by opening all the others. And just like the case you chose at the beginning, this case is chosen completely at random. It is also super unlikely to be the winning case. In fact, chances are both of these cases are actually losing cases. That can't happen in the Monty Hall scenario. But what about when we just considered the scenarios where you're left with one good prize and one bad prize? That seems similar to the Monty Hall problem. You chose one case at random, opened 24 cases that are all losers, and now you have to choose between the case you picked randomly at the start and the one case that was left unopened among a sea of losers. What makes that scenario different from the Monty Hall scenario? Well, in order to understand that, we're going to have to use some Bayesian intuition. I could try breaking out Bayes' formula, but numbers aren't really my thing, and they're not that convincing anyway. Hopefully it'll make enough sense without it. So, when you choose your case at the beginning of the game, it has some low probability of being a winner. As you open the remaining cases and see that they're not winners, you're gaining new information. You're learning something new that lets you make more informed probabilistic estimations. You can now be slightly more confident that your case is a winner, and that confidence increases bit by bit until you either open the winner, dropping your confidence to 0, or you get down to the final case, at which point it's a 50-50 bet. The key difference between this and the Monty Hall scenario is that, from your perspective, Monty's turn always looks the same. It doesn't matter what door you chose at the start, whether it was a winner or not. Monty is always going to open a door with a goat. You don't learn anything new about your door, so your confidence shouldn't change. It should still be a 1/3 or a 1 in 100 chance of being a winner. So, in conclusion, Deal or No Deal is not an instance of the Monty Hall problem. Keep your case or swap it, it makes no difference in the end. This wasn't my usual type of video, so I hope I was able to explain everything clearly. If you enjoyed it, consider subscribing and following me on Twitter, as well as checking out some of my other good videos. If you didn't, feel free to leave angry comments. Either way, thanks for watching.
Hello, ladies.
Hi, Howie.
Ooh, I love